Hi, I'm Sinyoung Cho. Today I'm going to talk about our global and longitudinal measurement platform specialized for detecting internet censorship. This is a joint work with other researchers at Stony Brook University, University of Massachusetts, and Carnegie Mellon ICLab. Internet censorship, which restricts access to specific web content, has been happening since 1996. Since then, it has become more and more common over the world. Reporters Without Borders issued an annual report on freedom of the press. In this map, the darker the color of the countries, the lower the level of freedom available to journalists. There is another map issued by Freedom House on freedom on the net, and we can see countries that are not free or partially free. From these reports, we can see that governments frequently control what information can be accessed by the citizens. Many works like these reports have been done with qualitative research methods and do not use automatic measurements, so they are not repeatable and scalable. Some censorship activities are apparent to everyone, like block pages. This block page is saying it is blocked due to illegal harmful information, and the others are happening without letting citizens know. As an example, researchers at CitizenLab found through internet scanning that deep packet injection meter boxes are installed in Turk Telecom's network and silently redirect user connection to download a nation-state spyware. With the meter boxes, they also blocked human rights and political content, including Wikipedia. But we have a lack of understanding of the behaviors of censors, thus we need a tool to monitor the extent of censorship. The monitoring will allow us to understand the behavior of censors, and this understanding will help us to defend against it. So how do censors block user access to web content? Before that, let's first think about what happens when we typed an URL in our browser. First, our browser looks up the domain name and gets an IP address. Then it carries out a TCP handshake. Once the connection is established, it started getting HTTP content to display. So now let's discuss how a censor disrupts the connection. First, a censor can notice the DNS query with the domain name and send back a fake IP address that gets to a user before the original response of a DNS server. We call it DNS manipulation. A censor can also notice the TCP handshake message with the web server name and send back a reset packet or send back a block page. We call them packet injection and block page. I'll be going into more detail about each censorship method later. Before going there, I'll talk about other studies in censorship research that have been done since 2002. Each censor has its own censorship policy, and it can change over time, so we need a longitudinal and global monitoring. However, many published papers are case studies of a single country at one point in time. They show details of measurements, but their approach is not sustainable over the long term on a global scale. INCOR, IRIS, and QUAC have a good broad range of location to be measured, but limited to detecting only one censorship method. These works have done well and give us some good insights. However, they could not give a complete view of censoring with continued global monitoring. One of the challenges of the current studies is to get access to vantage points. As we need to be inside the network to see how a censor behaves, it is difficult to measure censorship happening in the places far away from us. To solve this problem, many case studies rely on volunteers to run measurements. However, there are ethical concerns that volunteers can get into trouble for accessing illegal web pages on our behalf. Also, it is hard to extend the time period and the number of regions. While remote measurements such as QUAC allows good coverage on time period and countries, but it lacks detail. Apparently, there is a trade-off between coverage and detail. And another challenge is that due to lack of detailed measurements, existing detectors are error-prone. Thus, we built our own platform ICLab to fill this gap and give a comprehensive view of censorship. So let's talk about our platform in detail. ICLab offers global and continuous monitoring. It has been running since October 2016 in 62 countries. For vantage points, ICLab utilizes commercial VPNs and a small number of volunteer-operated devices. Using VPNs gives us some benefits. We can avoid risk to volunteers who used to run the experiments. Also, VPNs guarantee high availability, sustainability, and reasonable bandwidth in many different countries. Furthermore, the VPNs allow us unrestricted access to the network, unlike phone or web applications. But there is a limitation of using VPN. As you know, some VPN providers lie about their server locations. Thus, before we use the VPN servers, we first validate their location with our geolocation checker. If you want to know about how we validate the server location in detail, please refer to our paper and IMC paper in 2018. ICLab has 3 control nodes where we expect that censorship doesn't exist or exists relatively less. One in an academic network in the US, one in Japan, and one in the Netherlands. These control nodes repeat all the measurements that each vantage point performs. The measurements from the control nodes are utilized for censorship detection by comparing the measurements from our vantage points. Each vantage point tests connectivity to the website in the list issued by Alexa CitizenLab and Berkman Klein Center. And when performing measurements, ICLab collects data at all levels of network stacks, thereby offering reliable detections of network interference by minimizing false positives and false negatives. And with the collected data, ICLab detects 3 censorship methods that we discussed at the beginning: DNS manipulation, block page, and packet injection. And now, the rest of this talk is about how we detect such censorship methods. After that, I'm going to talk about our key findings. For DNS manipulation detection, ICLab requires DNS responses to the same DNS query from a control node and a vantage point. If a vantage point receives NS domain, but a control node receives an IP address, we classified it as manipulation. If there is a second DNS responses from different AS, this is a packet injection by unpassed sensors, and we label it as manipulation. If both a control node and vantage point receive the same IP address, this is obviously not a manipulation. But if only a vantage point receives a non-routable IP address like loopback, this is DNS manipulation. And now, the most difficult cases are when we receive different globally routable IP addresses from a control node and a vantage point, because this might be due to a CDN load balancing, not censorship. So in this case, we utilize the common observation that some sensors tend to map many blocked websites for a few addresses. For example, we observe a single IP address returned for many websites like Google or Facebook. In this case, we check URL to IP ratio. If the ratio is high enough, we are confident to label them as DNS manipulation. We also developed a packet injection detector. It avoids false positives by combining information from multiple levels of the network stack. Look at this figure. We classify packet anomalies by comparison to control nodes observations. We first find evidence of packet injections like payload conflict. And if a packet collision is found after successful completion of the TCP handshake, we check if only one packet has either its reset or fin bit set. Or we check if the payload collision matches a known block page signature. And if either or both answers are yes, we are confident these cases are censorship. When both a control node and a vantage point observe either a TCP reset or an ICMP unreachable packet, we conclude the site is down for everyone and this is not censorship. But if we observe this only at a vantage point, this may indicate IP-based censorship or a local network outage at the vantage point, so we label it probably censorship. And next, ICLab detects block pages with the predefined regular expressions of the previously known block pages. If we have regular expression in our database, we can always find the corresponding block pages. However, the challenge is to find the unknown block pages, and ICLab has two techniques to discover them by utilizing its PCAP and HTTP measurement. For HTML tag frequency vector clusters, we compute a tag frequency vector of each HTML, and for the other clusters, we apply locality-sensitive hashing to each HTML structures of web pages. Then we find candidate websites whose tag frequency vectors or LSH match those of our known block pages. So when there is a group of block pages generated by the same filtering software, they tend to have similar tag frequencies or HTML tag structures. So matching to known block pages can help us to find new block pages. We can also find totally new unknown block pages. For that, we compute URL to tag vector ratio and URL to country ratio. Then we sort the clusters from largest to smallest ratio and then inspect the entire list manually. By doing that, we found 15 and 33 new block pages respectively. As a result, we ran our three detection techniques over the collected data and observed 15,000 DNS manipulation, 143,000 packet injection, and 232,000 block pages. Now, I'll talk about our key findings: analysis by test list, by methods, longitudinal analysis, and other network attacks detected by ICLab. First, our results show that which web list to test can change our observation about censorship policy. In this table, we divided our results based on each test list. The table shows that the top 3 categories blocked by each country differ somewhat from one list to another. For instance, pornography is much less prominent on the country-specific list than on the global list. Secondly, we observed that censors use different methods for different web content. Maybe it is an attempt to conceal political censorship. This time we divided our results based on censorship method that ICLab can detect. From this table, we observed Turkey performs DNS manipulation to censor the domains of illegal or unethical and streaming media and download web category, but it returns block pages for domains of pornography and news and media. Also, look at this figure. It shows how often different censorship methods are used in combination. For instance, this group of bars indicates that users get redirected to block page through DNS manipulation. Each group of bars is mutually exclusive, and the sum of all groups is total. In Iran, we detected some URLs being redirected to a block page through DNS manipulation, but for many others, we detected only the block pages. Third, nearly 2 years of data allows us to observe change in censorship over time. From our research, we observed a slow decline in the number of censored websites over the world. It's probably due to increased use of HTTPS, but there was no decline in the countries with the most aggressive policies. Also, we observed a rise in the level of filtering from 3 to 5% in Turkey, which coincide with its political event. Although it is not visible in this chart, the topics censored also changed at this time. Prior to the rise, most of the blog sites in Turkey carried pornography and other sexual content. But after the rise, many other news sites were blocked. Finally, the broad and detailed measurements of ICLab also expose other forms of network interference, such as geo-blocking, user tracking injection in South Korea, and cryptocurrency mining injection that would have caused the client's browser to mine cryptocurrency. As a summary, I introduced our measurement platform ICLab and highlighted our key findings. First, different test lists can change our observations in censorship policy, and a censor uses different methods to block different web categories. And I talked about how censorship has changed over time. And finally, I illustrated that ICLab can detect other network interferences. As a closing, I want to introduce our ICLab website. From the website, you can find the recent information related to the project and also interact with our data with nice visualizations. If you are interested in it, please visit our website. That's all my presentation. Thank you for your attention.